Hey programmers, Alvin here. Right now I want to go over a JavaScript solution for this tree min value problem. And of course we'll solve this one a few different ways. I think I'll start by showing y'all maybe some iterative solutions. And so we'll just do some classic depth first and also breadth first along the way. Right? So you know you're going to need to iterate or hit every node within your binary tree. So just go ahead and set up either a stack or a queue. So I'll choose to start with a stack over here. So I'll say const stack equals an empty. And one thing I'll have to be aware of is looking at the assumptions in the problem. They tell us that we can assume that the input tree is not empty. And so that means I won't need to add a leading if statement checking if the top level root is null. So I can just go ahead and initialize my stack with the root node inside. Cool. And then from there, you need your main loop to iterate through the different nodes. So I'm going to loop while my stack is not empty. So while stack.length is bigger than 0. Cool, so if that's the case, then there are still some nodes to visit. And I begin a single iteration of this algorithm, let's say depth first, by doing stack.pop. So I remove the top of my stack, go ahead and call that my current. And then from there, of course, we need to check if our children exist. And if they do, I'll add them to the top of my stack, right? So I'll write a pattern like this. I'll say if, let's say current.left, that is not equal to null, then I can go ahead and push that existent child on the stack, right? So stack.push, and I'll push current.left. Written this a few times by now, should be second nature. And I'll do some same code for the right-hand side. And this is kind of my baseline of a depth-first traversal, right? But as I look at this current node and its value, I want to, by the end of my loop, have access to the minimum value within the tree. And so because I need to find the minimum value in this function, I'm going to use a variable that I'll update over time, right, to track the current smallest thing I've seen. So I'll initialize this as let smallest. I'm going to have to think about a good default value for this. And so I'll go ahead and initialize this to actually positive infinity. So if you're unfamiliar with some JavaScript, infinity is basically just a number that is guaranteed to be bigger than all other numbers except for itself, infinity, right? And the reason I'm choosing a big number like positive infinity for my default value for the smallest variable is because when I see any actual values of my tree, I know they're guaranteed to be less than infinity. So these numbers would replace my infinity. Just gives me a good initial value, right? That's a pretty common pattern, right? If you're looking for the minimum thing, then typically your default value is positive infinity. If you're looking for a maximal thing, then your default value might be 0 or negative infinity, depending on the problem you're trying to solve. And so with that default value, where do I actually want to replace it, right? And I'll choose to do that right after something leaves my stack. That way I only have to say it once. If I wrote it when I added my children into the stack, I'd have to say it twice, right? Which is kind of annoying. So I'll just check, hey, if current value, so be sure to compare the actual number value. Current value is less than the smallest, then I've just found a new smallest, right? So just replace that variable with current val. Of course, by the end of our while loop, we should just return that variable, right? And we should have the true minimum. So let's give that a shot, run these test cases. And this is our rendition of an iterative depth first, right? Awesome. So if you wanted to switch it up, you know, writing the breadth first is super trivial in terms of the change we make. You can just make sure you do stack.shift, right? Because that would remove the front element of your queue now. And if you push, then you're still adding it to the back. And I guess you should probably rename this guy to queue. So very minute difference. We'll test that. Give that a go. Cool, passes all of them. Nice. And one thing to note, so at least in JavaScript, there is no immediate, at least when I recorded this video, there is no immediately available like optimal queue data structure just baked in. Like you can't import it through a standard library. And so when you actually do the array.shift method, that line itself is going to run in O of n time, right? Because if you remove the front element of an array in JavaScript, it will have to actually shift all of the other elements over one position. In other words, index 1 becomes index 0, index 2 becomes index 1, and so on. And so technically, if you implemented your breadth first exactly like this, just using a regular array, and you shift out, then this would probably be technically like an O of n squared. solution, which isn't the fastest, but will be able to pass the specs. Typically, n squared for most problems is kind of okay, but you can avoid it if you want to get the blazing fast solution. But now let's actually go ahead and implement my favorite version, which would be a recursive version, right? Which is technically of the depth first, right? So we'll say const, what is it, tree min value? Yeah, tree min value. And to establish this one recursively, we'll always start with our base case, right? So we need some of these curly guys. So I'll start with my base case. I'll say if my root is equal to null, then that kind of means I have the empty tree. So what's like the minimum value in the empty tree? Well, that must be infinity, right? For the same reason we chose infinity before, right? It's just a good default value because I'm going to minimize in the long run. Cool. And now what I want to do is I want to make my recursive call. So if I call tree min value on my left child and I call it on my right child, I'll just think about what these function calls return, right? Although they're recursive, if these calls work, they should give me back the smallest value in the left subtree and the smallest value in the right subtree. So maybe just to be clear, I'll go ahead and save these system variables. So I'll say const, I'll say left min, and also this should be the right min, right? So I found the smallest in the left and the smallest in the right, but I also need to think about myself, right? I am root.val. So I need to choose the smallest of root val, left min, and right min, right? So you can write like a conditional, so just some if statements if you want. I think the best way to implement this in JavaScript is just to use the math.min function. So in JavaScript, you always have access to the global capital math object. It has a few useful methods on it. One we're going to find useful right now is math.min. And if you do that, you can pass in some arguments and an arbitrary number of arguments. So give me the smallest between root.val. Be sure to access the value because you need to give numbers to min, right? Smallest between root.val, my left min, and my right min. Cool. And this feels somewhat similar to the approach drawing we did, right? Where we had to choose the smallest of these three numbers. So before we run it, maybe you're unfamiliar with math.min. I can quickly demo that for you. So let's say I had some numbers. We had 10, we had 3, we had 6, and we had -12, and also 100. And if I console log what that returns, I'll just run this file as a script. So I'm not going to execute the test quite yet. So I should get -12 because that's the smallest. Perfect. And now I think we're ready to go ahead and test this. So our recursive version, there we have it. Cool. All right, so there we have our JavaScript walkthrough for this tree min value problem. Recommend you practice all of these different solutions and then pick a favorite, maybe just have it in your back pocket. That way you can always solve this problem in the future, right? So you should have no issue thinking about how to solve like a tree max value problem. And by now, we're getting pretty comfortable with trees. And typically, we're always going to fall back to either a breadth first or a depth first reversal. But in the next few problems, we're definitely going to look at some spin-offs and some variations on how we can accomplish more complex logic using these algorithms as our baseline. So I'll catch you in the next one.